Nuclear physics. In this video, we begin our discussion of nuclear physics. Nuclear physics is the branch of physics that deals with the structure of the atomic nucleus and its interactions. We will begin by studying the structure and properties of the atomic nucleus. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It's very important for the continuity of this channel. All atomic nucleus is made up of two types of particles, protons and neutrons. The only exception is the nucleus of the simplest atom, hydrogen, which is a single proton. We use the generic term nucleon to refer to either a proton or a neutron. The proton has a positive charge, the same magnitude as for the electron, and its mass is measured to be. The neutron is electrically neutral, as its name implies. The masses of the proton and the neutron are almost equal. Nuclear masses are very small. It is not convenient to use such small units. So for atomic and nuclear masses, it's convenient to define the unified mass unit, U, in such a way that the mass of one neutral carbon atom is given the exact value 12 unit. So, one unified mass unit is defined as the mass of one atom of carbon divided by 12. It is often convenient to express the particle's mass in terms of its energy equivalent. This can be done because mass and energy are related by Einstein's equation. Then, the energy equivalent to one atomic mass unit is given as follows. Masses can also be specified using the electron-volt energy unit. The relationship between electron-volt and joule is. So we can find the mass of one atomic mass unit in electron-volt as follows. Usually, the energies involved in nuclear physics are millions of electron-volts, mega electron-volts. So we express the mass in mega electron-volts. Nuclear physicists often use Einstein's equation to express mass in terms of the unit mega electron volts divided by c squared, as follows. Now that we know how to express an atomic mass unit in kilograms and in mega electron volts, let's also express the mass of the proton and neutron in these units. Pay attention because the calculations are very simple. The table below shows the masses of the protons, neutrons, and electrons. The size and structure of nuclei were first investigated in scattering experiments of Rutherford. If you need to review this subject, please watch the video posted in the upper right corner of the screen. We cannot speak about a definite size for nuclei because protons and neutrons also have properties. Then, their size must remain somewhat fuzzy. However, a rough size was estimated when Rutherford performed an experiment of scattering of alpha particle from the nucleus, which is considered as a point charge particle. In one of the experiments, Rutherford used alpha particles of kinetic energy 1.2 times 10 to the power of minus 12 joules, about 7.7 mega electron volts. He considered that in such a head-on collision, The kinetic energy of the incoming alpha particle is used to do work against the Coulomb potential of the nucleus. If we equate the initial kinetic energy of the alpha particle to the maximum electron potential energy of the system, alpha particle plus target nucleus, we obtain the distance d is the distance of closest approach between alpha particles and the gold nucleus. At this distance, the alpha particle momentarily stops. Solving for d, Rutherford concludes that the distance d is approximately 3 times 10 to the power of minus 14 meters. This calculation gives an upper limit for the radius of the gold nucleus, and Rutherford concluded that the order of magnitude value for the radius of a nucleus is about 10 to the power of minus 15. Because such small lengths are common in nuclear physics, a convenient unit of length is the femtometer, sometimes called the Fermi, and defined as 1 unit of length equal to 10 to the power of minus 15 meters. Since the time of Rutherford's scattering experiments, a large number of other experiments have shown that most nuclei have a spherical shape with an average radius given by the formula, where r sub 0 is a constant equal to 1.2 Fermis, and A is the total number of nucleons. Let us now get some estimates for the size and density of atomic nuclei. Estimate the diameter of the smallest and largest naturally occurring nuclei. The radius r of a nucleus is related to its number of nucleons, A, by the formula above. The simplest nucleus is that of hydrogen, A equals 1. So we replace A with 1 and performed the calculations. The largest nucleus is that of uranium-238. A equals 238. So we replace A with 238 and performed the calculations. From these results, we see that the largest nuclei, such as uranium, have a radius only about 6 times that of the smallest nuclei, such as hydrogen. The range of nuclear diameters is only from 2.4 to 15 Fermis. Estimate the density of the smallest and largest naturally occurring nuclei. We can picture a nucleus as a small positively charged sphere. The simplest nucleus is that of hydrogen. So we can calculate the volume of hydrogen, and then we calculate the volume for the largest nucleus is that of uranium. We know that the density is equal to mass divided by volume. So we perform the calculations. These results suggest all nuclei have nearly the same density. Nucleons combine to form a nucleus as though they were tightly packed spheres. Compare the density of nuclear matter to the density of ordinary matter. First, let's compare the mass of a proton to the mass of an electron. We can see that the mass of a proton is 1 1,836 times that of the electron. This result suggests that almost all the mass of an atom is in the nucleus, and for our estimate, we can say that the mass of the atom is equal to the mass of the nucleus. We now find the ratio of nuclear density to atomic density. Atoms have a radius of about 10 to the power of minus 10, and nuclei on the order of 1 Fermi. The nucleus is 10 to the power of 15 times denser than ordinary matter. This is a consequence of the fact that the nucleus occupies only a tiny fraction of the volume of an atom. A grain of sand has approximately a volume of. Calculate the mass that a grain of sand would have if it were made of nuclear matter only. In this example, we will use the grain of sand density as the nuclear density. After performing the calculations, we arrived at an amazing result. Nuclear matter the size of a tiny grain of sand would have a mass of about 1,000,000 tons.